Hi and welcome. Today I'm going to talk about the Abaqus PRF model and specifically how you can use user creep models from the PolyUMod library within the PRF model in Abaqus. So in our recent version of MCalibration and PolyUMod, we support some specific creep equations that doesn't come with Abaqus, but they sit within the PRF model. And the way you use this is, as you can see in the example here, you just set up a hyperelastic material, and then you have star viscoelastic nonlinear law equal to user. And that's how you can specify one of these user-defined creep equations that come with the PolyUMod library. But the stress calculation is done using the PRF model in Abaqus. So it's kind of a hybrid PolyUMod PRF model approach. And this has some advantages. The advantages is that you can use different creep equations than will come with Abaqus. And there's a specific equations for the creep response that I have developed that I think are better in many cases. The first one here that we have implemented is a Bergstrom-Boyce model, which is already available, but this one has pressure dependence, and that can be very useful sometimes. And the second one is a power law dependent creep model, which is also available in the PRF model, but this version of it is more advanced. It has yield evolution in addition to that, and pressure dependence in addition to that. So you can do some really cool things. So I'm going to demonstrate how you would use the PolyUMod flow equations within the PRF framework in Abaqus. So I'm going to show you that using MCalibration. So I have some experimental data. This happened to be for a CPVC thermoplastic material. You can see stress strain curves here. Uniaxial tension followed by unloading, and I used this by simply set a material model, and in this case within the Abaqus section we have the new ones that I just mentioned, and the one I want to focus on today is the PRF3 network YO power YEP, so yield evolution pressure dependence. So if you select that, we'll just get the parameters as you typically do here. And you can calibrate it as you typically do, and I already have performed the calibration, and you can see in the dashed lines here that this prediction looks reasonably good. It's about the 10% error in average, but it has the softening after yielding that you see in the experimental data, which is pretty exciting in many cases. So how does this work? How do we actually use it? Well, this was all calculated using MCalibration. I can create a load case here that are going to use Abaqus to calculate it. So I turn those off. I take the first one. I'm going to duplicate that, and it's going to be down here. I'm going to rename it to Abaqus. So it's going to be solved using Abaqus. I'm going to go to miscellaneous, solver, Abaqus standard. Now, this will then be calculated using Abaqus. There's another thing I want to do to make it run better. See that this particular load case has 1,823 time points. So if you have the default setting here, MCalibration will instruct Abaqus to take exactly that many increments, and that's unnecessary in a case like this. So I'm going to switch it down to 200. That's going to make it run a little quicker. And might as well change the color of this a little bit while we're at it. So I'll take some kind of color like that to make it look a little different. And then I'm going to just run this again. And this time when I run it, the first load case is using MCalibration as the solver. That's already done. It takes virtually no time to calculate. The second one here is using an Abaqus calculation. So it launches Abaqus with this predefined material model that is down here. And we'll take a look what that looks like once the simulation has finished. And that's it. The simulation finished. We see that the brownish line is very similar to the red line. That means that Abaqus solution and the MCalibration solution are the same as they should be. We can now take a look at the actual files that were generated. So here they are. I have it saved in this directory here. And the Abaqus file that is the master file looks like this. It's a single element simulation, as you can see. It has an amplitude defining the load history, and it has an input file here to specify the material model. So we'll take a look at that after I scroll to the bottom. So it's a start visco step at the bottom as well. So let's open the actual material model. Here it is. And this is the material model. This is how you would use this user-defined PRF model. It has hyperelastics or viscoelastic law user, and there are two of those, and these parameters were defined using MCalibration. You can then put this into your any Abaqus simulation you use, and it will use the PolyUMod version of the PRF creep model here as it calculates the stresses. So that's the feature that I want to demonstrate today. Let me know below if you have any questions.